Hey, hi guys, this is Faizan and welcome to today's session. Today we are going to understand greedy algorithm, right? And before I start, can you guys quickly confirm in the chat if I'm audible or not? Is everything okay? Can you see me? Can you see my screen? Can you see the pointer over here? If everything is good to go, just give me a quick confirmation in the chat that I am audible, right? Yeah. So this is going to be a short session, 30-minute session, and we are going to understand greedy, and we will also see some problems based on it. Okay. While we wait for others to join, let me give you a quick tour of how our academy looks like. So we all know about it, right? If you have been attending sessions, that we know all about it. So it's a great, so-called Great Learning Academy, the initiative that we started. Now, what is in this academy, what are the things that you can look for? Okay, so basically it contains all the live sessions that are there. Right now I'm taking this greedy algorithm, right? Ram is taking design portfolio for freshers, right? And all these live sessions are there, right? Plus what else is there you can have all the trending courses, and these are all the courses that are for free, right? And you see, these are all popular courses. The introduction to digital marketing is there, machine learning in Python, that is in Hindi as well as in English. Okay, so all these sessions are there. You guys can check it and go through these sessions, and after the completion of these sessions you have to answer 6 questions correctly out of 10, and to get your completion certificate. Once that is done, you can add those things into your resumes, in your LinkedIn profiles and everything, right? Cool. So what else is there? You can also search for PG or career transformation programs that are there. You just right click on it and open it a new tab. There you have it. These are all popular courses, right? These are all paid courses, guys. So if you are if you are looking for a career change, and if you're looking to pay for it, and you want to get a good decent job, so you can call us. The number is on the in this corner, and we have programs related to AI, machine learning, management, cloud computing, cybersecurity, and software development, as well as design thinking. Okay, cool. So you can once the session is over, you guys can check it after the session is over and go through it. Now if you're not willing to pay anything and you're looking for free courses, we have free courses available as well. Just browse through it. Okay, browse all courses and you will get the courses. Okay, done. So with that being said, let's continue our session and let's understand what are the things that we are going to understand. First, we are going to cover what is an algorithm. So we will see how algorithm works, what are the things that you should know, right? So these things will be covered. Then we will understand greedy approach. What is the greedy approach? What are its properties? We'll talk about when to use greedy algorithm, and is it always a situation that you will always get the optimal solution in greedy approach. Then we will talk about 2 problems, and we will see how we can implement this greedy algorithm. Okay, cool. So you can see me. Okay, great. So now let's talk about what is an algorithm. So basically it's a step-by-step procedure or approach that one can take in order to find a particular solution, right? If I'm looking on this side, guys, that means I'm looking at your chat. So keep interacting and try to make this 30-minute session as interactive as we can. Okay, so cool. So step by step, right? Step by step, and these steps need to be optimal in order to get a crisp solution, right? So once you take the steps, and you need to check, okay, if this is the optimal solution. Okay, now you also need to take care of this thing, that this is the algorithm that whatever you write should be for non-technical persons as well. You don't write any program or language independent code. Okay, you have to write not language independent, you don't write any language dependent code. Okay, it should be language agnostic. Okay, it's free from programming language constructs. Okay, you should not be using terms like what complex terms like arrays dot sort. Okay, we are then sorting the arrays. You should keep it simple as possible. Okay, and once you have done with the algorithm, right, once you created the algorithm, then you look for, is this the efficient one? Is this algorithm the efficient one? Okay, no, then you don't waste your time in programming it, right? In whatever language you want. Okay, so same thing happens for any problem when you're working as a software developer, right? So therein also, you don't just go and program your code. You just first write the pseudocode or the algorithm. Okay, so you write the algorithm, and then you check for different constraints means conditions, right? You check for different condition. Okay, is this condition satisfying? Is this condition satisfying? Can I make this much more as efficient as possible? Is this the efficient algorithm? Let's suppose you are building an algorithm which works in order n square, right? Big O of n square. Can I do better? Can I go for n log n? And once I'm going for n log n, can I do any better than this? if I'm using some space, let's suppose you're using now the space of big O of n, and now can I do better? Yes, you can. These are the things that you should look for. Okay, can I do better? Okay, so that is how you reach to an efficient algorithm, and once that is done, you just program it, and that's it. It can be in any language. Okay, done. And what else? Now this is all about algorithm. Okay, now let's talk about greedy algorithm. So now greedy algorithm or greedy approach works in such a way that you will look for local, what is known as local best, or you can say that local optimal, right? So whatever is the local optimal solution. So let me give you an example here. Okay, or let's try to first cover these 3 points, and then I will give you an example in a different slide. Okay, so now what is this? So this is greedy works in such a way, guys. You need to interact, guys. If you are not able to understand anything, just ping me, just write it in the chat. Okay, so it works in such a way that it looks for local optimal. That means it will look for, let's suppose we are here and we will look for these two situations. Okay, is this situation best or is this situation best? Depending upon this local, we'll take a decision. We'll take whatever is this whatever is the scenario, we take the best at this particular point. Then moving ahead, we again take the best. Now we take this best conditions or best optimal solution at that particular time, that is the local optimal solution, in order to reach the optimal solution that is global. So you'll take optimal decisions at each step in order to reach a global optimal solution. I know this is difficult. This might be something that is going over your head. I will explain with the help of example. Now it is different from backtracking, right? In backtracking, I will take a session tomorrow on not tomorrow on Monday at 12. I will take a session on backtracking. It works in such a way that it will look for all the possible paths, but in this greedy, it will never it's such a paradigm that it will never recheck its options. Okay, or whatever is the choices that it made, it will never recheck them, it will never traverse back. Okay, and it is not guaranteed that it will always give you an optimal solution, although you are taking optimal you are making local optimals, you're trying to find the local optimal solution, but it will never give you a global. There might be cases wherein it might not give you the optimal solution. Now let's take an example and things will be much clearer. Okay, so let's suppose we have Urvashi, right? And Urvashi has been given coins, right? Let's suppose she has been given 50 paisa coins, 30 paisa coins, and 10 paisa coins. And now I'm telling Urvashi, okay, Urvashi, do one thing. Here's a customer, and you need to pay him in such a way that there's a sum associated with it, right? So you need to pay him 80 paisa, and you need or 90 paisa, right? Okay, 90 paisa. Okay, and you need to pay him in such a way that you should utilize as minimum number of coins as you can. Okay, so what Urvashi did, so there can be many solutions, right? Urvashi can pay him 10 paisa coins 9 times, right? 10 paisa coins, or Urvashi can pay him 30 paisa coins thrice, right? Or she can pay him any number, right? But no, greedy, whatever is the problems associated with greedy, right? The things that it will never or it will not backtrack to its optimal solution, or in order to find the optimal solution, there is something that is known as dynamic programming. That is where your dynamic programming comes into picture. Now backtracking is not optimal always. Why? Because it looks for all the possible paths, wherein you need to be greedy in making your choices. And now whatever you took the choice, it might be the case that it is not the best optimal solution. So what you do, you will use your dynamic programming, and that at that time it will see, okay, now we're not getting the optimal solution, let's go back and see. Okay, you can say that it's a kind of a backtracking, but therein backtracking will check all the solutions, all the conditions, but here we will be greedy. In greedy plus backtracking, you can say that it is dynamic programming, but not backtracking, because there is all the things that you will traverse all the paths, you will look for all the paths. That is not the case here. Okay, so now what is happening? So Urvashi tried to pay him with 30 paisa coins, 30 paisa coins, 30 paisa, 30 paisa, and thus making it a 90 paisa, right? But these are not, you might say that, okay, this is the solution, but I want to give it, and you see here the output is 9. So she will be using 9 coins, right? And if I give him some other choices, let's suppose she is giving him 30, and then 10 paisa coins. How many are left? 6. Okay, so she's using 7 coins. Now the best solution that you can think of is that you can either go for, right, you can go for 50 paisa coin, then a 30 paisa coin, then a 10 paisa coin, thus making it 90, and you will get the optimal solution. And you will, even if you are using 30 30 30, in that case also you will get 3 coins, right? You're using only 3 coins in order to pay him, right? Now here you can understand, okay, this is the optimal solution, and we are making a choice that should we go for this or should we go for this, depending upon which one is greater, and it should be obviously less than the 90 paisa. Then we will give that customer the coins, right? Done. But here you can see that, okay, we are able to find the optimal solution. But there can be cases where even though you are making a choice, right, you are making a choice, still you won't be able to get the optimal solution. Now let's see what that example is. Let's suppose I have given a tree and it contains 10, then there is 4, then there is 6, or let's name it 3, and now let's name it let's do it 27 over here, and 15. Okay, and here what we are doing, we're doing 10 and 10, we're going for 16. Okay, this is a tree, and now I told you to give me the maximum sum that is there, in order to try to find the maximum sum that is present in this tree, right? What you will do, you will start with the root node and you will check, is this greater or is this greater? So you are making the local choices here. Is this greater or is this greater? So what you do, you find the greatest, because this is how you perform this operation. This is how you look for greedy solution. You make a choice. Should I go for this or should I go for this? Now 10. Now you're going for greater one. Obviously that will result in the greatest or the maximum sum that you're looking for, right? So you will go for 10, right? And you will go for 4. Now you will go for 4. Now you'll check, is this greater or is this greater? Now you'll see, okay, is the 16 is the greatest number, and you will be able to find the solution, and the output is 30. But is this the maximum output that you can get? No, this is not the optimal solution, because there is one more path, that is 10, 3 and 27, which gives you 40, which is the maximum sum, right? So now you see, even though you are making local optimal, you are trying to find the local optimal, right? You're looking for the optimal solution locally, and in order to get a can we solve this problem in big O of n? Yes, Ravi, yes, I will show you how we can solve this in big O of n. Okay, there has to be one constraint, else it won't be, you won't be able to, else you can use dynamic programming, which is not the objective here. We are trying to cover greedy approaches. Okay, we are trying to see how to perform greedy operations, or how to perform greedy, how to look for a given a problem, you're trying to solve it using greedy approach. Okay, you are being greedy. So this is the greed that you're doing. Okay, you are looking for a maximum number based on this local situation, right? And then same goes for here. You're looking for the best, you're looking for the greatest number at this particular instance. So locally you are finding the greatest numbers, and in order to reach the optimal solution, but here it fails. So that is why I have said in the earlier slides that it is not guaranteed that you will always reach the optimal solution. Okay, done. So now what are the two properties that every greedy algorithm has? One is the greedy choice. So you look for a choice, right? Whenever you was 10, you looked for greedy, you looked for a choice, right? And that choice was, should I go, or we should go for a greater number, right? We went for a greater number, that is the data on this node is 4 and data on this node is 3. So you made a greedy choice, right? Because you're looking for maximum, so you made a greedy choice, should I go for this or this? So choice will be always there. And what else this will be there is the optimal substructure. Now what is that optimal substructure? Because making a greedy choice at every position, your output is dependent on those positions, right? Or let's take an example, that same example. So you had 10, you had 4, and you had 60. So all of these are local optimal, right? And this is where this is what you mean by optimal substructure. So those optimal solutions that were there in every iteration that you did will be part of your optimal final solution, right? Optimal final solution, that is your global solution, right? So that is what you mean by local this optimal substructure. So these optimal solutions will be part of your result, or will be part of your answer. So these two properties will be always there. Okay, is this thing clear, guys? Does this is this making sense? So you look for a choice, and then you look for the, you will understand that, okay, whatever we find locally will be there in our resultant, or we will be there in our solution when we look for the final solution, that is the global optimal solution, that will be there. Okay, is this thing clear? Quickly confirm in the chat if everything is clear. Then we will look upon one example and see how we can do it. Okay, quickly guys, just write a yes or no. So these are all the things, right? The properties, greedy approach, optimal substructure, where it fails and where to use it, right? When we can use it. Then also we have seen what is a greedy algorithm. We went through it. We checked, okay, whenever we are looking for we are looking for something that is the best solution at that particular time, that is local optimal. And in order to whenever we are finding these local optimals, we are trying to find for the global optimal solution along with those local optimal solution. That is where your substructure comes into picture, right? It's not guaranteed that always you will find the optimal solution, and it's a programming paradigm wherein you never backtrack. Okay, okay, cool. Now what else is there? Now let's look at the problem, and the problem is such that we are looking for, these are all the activities. So this is also known as an activity selection problem. So you have been given an activity, right? So these are all your activities, A, B, C, D, E, and F. So I told you that you need to, yes, you can say that we are maximizing the profit, yes, at that particular in that particular problem, yes. So now what you are doing, we have this number of activities, and in these activities we have a starting point and we have an ending point. Now you need to find a way that, moving from activity 1 to the activity F, you need to find a way that you need to maximize the number of activities that you can solve. Okay, you need to maximize the activities, right? So I want an answer in such a way that you should be able to perform maximum activities. Now one solution can be, okay, you will go and traverse, and that might take time. Okay, so another solution is how you can use a greedy approach. So obviously now if the end points are solved, if the end points are sorted, right, the end are sorted, so how would you sort it? So you will write 1 2 4 2, then you will write 1 6. Okay, we are sorting with the help of this end. What is the starting point and the ending point? Okay, we are sorting it with the help of ending points. Okay, so 1 6 is there, then 5 7 is there. These are all, this is your start and this is your end. So we are sorting with the help of this end points. Okay, so once you will be able to sort this, so we'll write 8 9 and then 10 7. So this is an activity selection problem. Okay, so now once I did a sorting, so now I know, okay, based on this, because I want to maximize my I want to maximize the number of activities that I will be able to perform. So depending on the minimum one, right, I'm sorting it in such a way that I can pick the minimum. So because once I will be able to pick the minimum, only then I can maximize the number of activities that I can solve, right? Makes sense, right? So now what I did, I sorted this based on the end time, and now what I did, I checked if this end time, that is here, is less than or equal to this, that means I can perform this activity. That means these two activities can be solved. Similarly, when I look for this 4 and I checked with this starting point, obviously this has already passed, so I cannot perform this operation, or I cannot perform this activity, right? And similarly, I check this 4 with this 5 now. Okay, now this is less than, obviously this is less than, that's 5, so I can perform this as well. So also D can be done, right? So now once I am done, I will check, is this 7 less than 8? Yes, it is, so I can perform E as well. So 9 and 7, no, I cannot perform it. So in such a way, while I am sorting this, I was able to perform this entire, I can solve the number of activities that I can solve in this, out of these activities are A, B, not C, then D, and then E. So I can solve 4 activities. Okay, hello sir, please, I can't find getting started menu on GL portal. How can I fix it? Okay, what I will do, I will let this issue know, that this issue to my team, and I will see what we can do. Okay, so as if now I cannot give you any commitments that it will be solved, it can be solved. I will look into it. I will tell this thing to my team, and they will look into it. Okay, how you can look for, okay, the starting menu. Okay, cool. So now in this way, I was able to solve these activities, and number of activities that I maximize the number of activities that I can solve are 4. Okay, now let's see what are the things that are there. So now In the main, let's suppose all of the, I will try to reduce the time complexity. I'm saying that the output that is there, the beginning array and the ending array is sorted, okay, just to reduce the time complexity. Now if they are not sorted, you need to sort them, and that will take n log n time, okay. So for now, let's suppose that these are sorted, and now what we can do, I'll just clear my screen. Now once these are two sorted array, I find the length, and I will go for this solve, that is this method, and I will see what we can do with it. We have two iterators, I1 and I2, and we are passing this b array, e array, and the length, okay. Now what I have, obviously, now the first activity, now why I'm starting with this, because I will always go for this first activity, because I know for sure that this will be the minimum activity. This is the minimum time, or okay, the end time is minimum, and based on this end time, I have a maximum probability that I can solve further activities, because this is the minimum end point, okay, because I'm sorting it. So I know for sure that this activity will be always in my solution. So that is why I have my answer as 1, right? And then I will start iterating. Now this iterator I is 0, and now I will iterate from the first index, that is this index, because I know for sure that this will be always in my answer. So I will start from this. So my one iterator is over here and another is over here, okay, in this particular array. Okay, now let's solve, let's erase this. Let's erase everything, guys. Okay, so now what we are doing, yeah, so we have this array over here. Let me put it in an array form, and let me pick up the values that were there. So 1 2 1 5 8 7, 1 2 1 5 8 and 7. So what else is there, in accordance with this, 5 8 and 7, okay. So what are the values? So those are 2 4 6 7 9 10, 2 4 6 7 9 10, 2 4 6 7 9 and 10. So we have one iterator over here. That means I will be pointing to this, I1, and I2 will be pointing to this, okay. And similarly, these will be pointing to this, because depending on this, we will pick up any of these two things, okay. Done. So now what we are doing, we are iterating through it once, and we are starting our I pointer from here. And now what we are doing, we are checking if b, that is this array, and this is the end array, right? We are checking if b of I2, that is b of I2, is it greater than or equal to e of I1. So I told you that these I1 and I2 are two iterators, and they are pointing. So we are checking same thing that I already told you. Is this I1, that is e of I1, is less than or equal to this? It is equal to. So what we do, we updated our I. Now I1 is pointing to this, I1 is pointing to this. We updated our I to I2, that was pointing to this. Now I1 is pointing to this. Sir, how to be perfect in dynamic algorithms? So basically, dynamic programming is again a different paradigm. We will try to cover it in the coming sessions, guys. So basically, that is something that is related to memorization. So memorization is nothing but storing your values that are already calculated. So in order to reduce the time complexity, so that in backtracking, what you do, you go back and calculate each and everything from the scratch. So what memorization does, what storing does, you don't have to go back and traverse back, and you just go into that particular array. Basically, we always pick, there's a, or you can say that there's a standard of using an array. So what we check, okay, is this already present in our array? If yes, then we pick something that from that array, which is already calculated, so that we don't traverse back and we don't exhaust that much time again in order to calculate that, okay. So now same thing we are doing, we are updating our I1, and now we are our answer is, because we want to calculate the number of activities that we can solve, okay. We updated our answer, and our answer is 2. So we can solve this, we can solve this. Now once we are out of this, we are updating our I2, so I2 will be here. And now again we check, is this 4 less than or equal to this? No, it is not. We just move ahead, because our I will be here as it is, and our I2 will be here, okay. Now we check, is 4 less than? Yes, it is. Now I2 will be updated to this position. We are skipping this element. Our I1 will never traverse to this, because we are traversing with the help of I2, that will be traversing on beginning array, and this will be traversing on the ending array, okay. Makes sense. Now we have reduced our time complexity if the two arrays are sorted to big O of n, that is linear time complexity, because we are already traversing single time, okay. We are already traversing each element once, that is from 1 to n, okay. That's it. So this is the output, okay. This is how you solve this problem using a greedy. So now what was the greedy thing that you did here? So you sorted this, and based on that sorting, you calculated, okay, you were greedy that, okay, if my array is sorted, if I'm picking up the minimum activity that is solved first, right? So at the first activity, that was from 1 to 2. So this 2 was the minimum element that can be there. and it will be always there in your activities that you will be able to perform. So this is the greedy choice that you made. And obviously now you're solving this and you're solving this, obviously then A and B and D, these are all the optimal solutions that you were able to get, right? Sir, please explain I2 and I1. So these are I2 and I1 are nothing but your iterators, guys. So these are iterators which help you to traverse. Okay, so basically what is happening, let me just pick it again. So now what is your array doing? So this is the I1, I2 is traversing from second element, because you know for the fact that first activity will always be there in your solution. So I2 is for beginning array, I1 is starting from the first index, okay, for the ending array. How? Because you see, you have only log n. Your the solve method is only traversing from I to L. That is the length of this. Is nothing but the length of the array. So you're only traversing once, right? You're only traversing once every element. So from 0 to n. So one by one you're checking, and that's it. Done. You're done with the algorithm. So that is why linear time complexity. Because I am taking this thing, one constraint in picture, one constraint into picture, that these two arrays are sorted. So you don't need to sort. If these two arrays are unsorted, then you need to sort them, and then your time complexity will be big of n log n, because for sorting this is the time that you require. Okay, done. So now this is how you solve it, and I1 will traverse, and it will help you to check it help you to compare this element with this element. And now if this element is not less than, this element is greater than, that means you have already passed this starting point. So you will not check this, and this I will be still here. You will iterate, you will update your I2 to this position, then you will check, then you update this to this position, that is skipping this element because this was not there in your solution. Okay, done. So now let's see the other example that I was talking about is when Arushi was giving the coins, right? So you know, you need these are all your denominations, that means 50 paisa, 30 paisa, and 10 paisa, and the sum is 90 paisa. How we can solve it using a greedy approach? So again, we'll take into this condition. First we'll sort this array. Why? Because then what we can do, we can find the greatest denominator that we can give off. Okay, so the greatest, once this array is sorted, so 10, 30 and 50, this array is sorted. Now we will traverse backwards and check, is this 50 that is there? We will traverse backwards, because then we will be able to find the maximum denomination that is there and compare it with our sum. Okay, we'll see, is this 50, is this 90 greater than this 50? That means, okay, we can subtract and we can pick this 50 paisa A, because this is the maximum. So once we are maximizing our denominations, that means we can minimize our number of coins, right? So obviously if you have 150 is your solution, right? So that is, so it's big O of n, that is 0. No, not 0. It is big O of n, that means linear time complexity, not 0, that is 0. It's a big O of n means that it is a constant. Big O of n, this is a big O notation, that means this is the worst case time complexity we are talking about. Okay, so now obviously if we have 150 paisa to be paid, then we can go for 50, 50 and 50, because we are maximum number that I can give is 50, right? We should not look for something that is less than. Now once we are subtracting this 50 from our 90, we will be left with 40. We'll again check, is 40 less than 50? No, it is not. Now we update our minimum, we traverse backwards, and we look for, is this 30 that we can pay, right? Is this with the help of this 30 paisa, can we subtract something? Yes, we can. We subtracted it, now we are left with 10. Is this 10 less than 30? No, it is not. Now what we will do, we'll traverse back, and let's see how we can do it. Okay, so again, taking into consideration that this array is sorted, right? This is a static array and this is sorted. If you want to sort it, you can again go for n log n. The time complexity for sorting them, that will be n log n. We're calculating the length of the array, done, and this is our main. We are trying to find for this sum is 90, and then we will solve this. We call this method that is solve. Now in solve, this is simple, right? And our answer is 0 because we don't have any denominations right now. So we are looking for 10, 30 and 50, and the sum is 90. Okay, that we want to give. Okay, this is our 0, 1, 2, 3. This is our array. Okay, now what we are going backwards. That means we are first, our I pointer is at L minus 1. Okay, so what is this L minus 1? This will be your length that is here, because we have calculated this length over here. That means you see this L is a static point, and now it is equal to coins dot length, okay, which is nothing but your L. So L is length of the array, which is pointing to here, I is pointing to here. Now what we are looking for is sum greater than coins, right? Coins dot I, that means Is our sum is 90 greater than 50? Yes, it is. What we did, we updated our answer. That means first coin has been given and we subtracted this from sum. So now our sum is 50, not 50, 40. Okay. So this is how you calculate it. And in the worst case, this can go for order of n square. So now we have n log n and we have big O of n square. So obviously big O of n square will be taken into consideration because we always go for the maximum one, because whenever our input size, that is the number of elements, will increase, this term will be less than this term. Okay, so that is why we'll take into consideration, and our this array will be we will get the output in big O of n square. Okay guys, so this slide deck will be shared with you guys, and this is it from this session guys. Thank you so much. If you have any doubt or anything, you can just write it in the comment section. You go through this because we are just subtracting it. Once we are subtracting it, we again check, is this sum less than 90? Now it is not less than 90, so we are out of this while loop, right? And now what we will check for here. Now once this is done, we update our I will be pointing to this. So is sum greater than? Yes, it is. Sum is greater than 930. We'll check. Yeah, I'm doing that. Okay, so is this sum greater than 30? Yes, it is, right? We subtract it from the coins. That means our coin, this sum will be 10 and our answer will be 2, right? 2 coins have been used. Now we again check, is this sum greater than 10, greater than 30? Is 10 greater than 30? No, it is not. We are out of this while loop. We again traverse backwards. Our I will be pointing to this now. So 10 again, yeah, is the largest one. Yes, n square is the largest one. So that is why we go for big O of n square. We check for this. We calculate, okay, is this 10 less than or equal to coins? Yes, it is. It is equal to. So what we will do, we subtract it. We are at 0, and now we answer will be updated to 3. Done. Ravi, yes, it is the largest one. That means in terms of if you try to calculate whatever is in n and whatever is in n square, the number of operations that will be performed in n square will be greater as compared to n log n. Okay, so n log n is much more efficient time complexity. N square is a little bit on the greater side, that the time complexity n square is greater. Okay, so n log n is just for sorting if you don't have a sorted array. Okay guys, so this is it from this session. I hope you enjoyed this session. Do solve these problems and do implement it. The language that I was using was Java. You can implement it whatever language you want. Okay guys, so these are the most important questions based on greedy approach. Okay, now there is one more problem. There is one more problem in this, that it is not always that you find the optimal solution when you are performing these denominations. Okay, so if you will see that if you have something that is like this. Okay, let me just pick up the question. So let's suppose you have 1, 3, 5 and 6. Now you're looking for the maximum optimal solution, right? 7 and 11 and then 1 and okay, so you you just figure out there will be some cases on some denominations that it won't perform well. It won't give you an optimal solution. You need to check that, and it's your homework. Okay, there will be a solution. I'm telling you that there will be a solution, but it won't be an optimal. Okay, for this particular problem, that is when you're trying to find the denomination, there can be some cases wherein it won't give you an optimal solution. Okay, so that is the drawback of greedy, that it won't always give you the best optimal solution. So that is why this is not used that much, but yes, it is there and you should learn it, and based on this we can just perform well based on or the whatever the drawbacks were in this. We solve those drawbacks with the help of dynamic programming. Okay guys, thank you so much guys, thanks a lot, and I'm dropping off from this session. I hope you enjoyed this session, and do practice. Okay, it's all about practice guys. Algorithms and data structures, it's all about practice. Okay, now try to solve different problems. There are Huffman coding is there. There is Digestra, you have prims, finding the shortest path, right? So you all have these algorithms which are based on, you can use greedy approach over there. Okay, all right, thank you so much guys, and I'll see you on Monday wherein we talk about backtracking. Okay, thank you.